Hello, everyone, and thank you for attending today's webinar. The webinar today is for the 2020 ACEEE Summer Study for Panel 1, Residential Buildings, Technologies, Design, Operation, and Industry Trends. The title of our webinar today is In Search of the Best Residential Technologies and Solutions, and today we're going to be talking about not just some great residential technologies, but also how to optimize the design and installation of those technologies. My name is Sharon Metzger from the Pacific Northwest National Laboratory, and I, along with Vladimir Kajkin from the National Association of Home Builders, will be your moderators today. Before we begin, I have a few housekeeping announcements. Your screen is customizable, so feel free to make the various windows as large or as small as you would like. You can even minimize them to drop the menu at the bottom of your screen. Click through the widgets at the bottom of the screen to make sure you aren't missing any options that are available. Presentations can be downloaded as PDFs from the presentation list in the menu. Attendees are in listen-only mode, but you can submit questions through the Q&A box at any time during the webcast, and Vladimir will be helping to facilitate that. The presenters will respond to questions throughout, but mostly at the end of the presentations verbally through their answers. The Q&A can be accessed in the menu at the bottom of the screen if it's not already visible. All presentations will be available for on-demand viewing within a few days of the Engagement Hub. Later this afternoon, after the panel sessions, informal sessions and social times will be offered through Zoom links. To access those sections, you'll find the links in the session icons on your menu bar. On behalf of ACEEE, we wish to first recognize and thank our sponsors for this event. So for the gold sponsors, we have E4 the Future, Energize Connecticut, Eversource, National Grid, SMUD, SoCal Gas, and United Illuminating. For our silver sponsors, we have ComEd, the Energy Coalition, Energy Trust of Oregon, Johnson Controls, NIA, ON Semiconductor, Samsung, and TRC. For our bronze sponsors, we have Guidehouse, NYSERDA, Opinion Dynamics, and BEIC. And now I would like to introduce our distinguished panel of speakers. They are Greg Futenhauer from Franklin Energy, John Proctor of Proctor Engineering, and Catherine Dayam of Exergy Consulting. Our first speaker is going to be Greg Futenhauer from Franklin Energy. Greg has received his BS in engineering with a focus in energy resources from Humboldt State University in 2015. He also holds a certification in data science. Since 2015, he's worked in a variety of areas, including the Lighting Africa Project, the Biomass Research and Development Initiative, and he's a lecturer at HSU. His main focus has been on energy usage patterns in ZNE buildings in California, where he's been a lead analyst under Redwood Energy, Build It Green, and now Franklin Energy. He lives in Reno with his dog, Loki. Greg, I will pass it to you, and you can go ahead and get started.
Thanks, Sharon. Yeah, it's really a privilege to be here at my first summer study. Today I'm going to be presenting on energy usage patterns in all-electric ZNE multifamily in California from a select number of sites. I'm only going to be able to cover a very tiny fraction of what we've been studying over the last 6 years, so please reach out to me directly. My email's on the bottom there if you want to dig in deeper, if you have follow-up questions. So there's sort of 3 papers intertwined in this work. I'm going to be primarily focusing on paper 924 for this presentation, but there's 2 other papers in this year's summer study, including paper 705, which is titled Hitting the Duct with Heat Pumps, and paper number 737. So I'd encourage you to go look at those as well. I want to briefly acknowledge the rest of our team. Everyone here had a big hand in getting this stuff to ACEEE. This was a partnership between folks like myself at Franklin Energy, Redwood Energy, Nehemiah Stone from Stone Energy Associates, 2050 Partners, and the Association for Energy Affordability. So first I'm going to talk about project goals and timeline. I'll go over an overview of the sites. I'll talk about instrumentation at least briefly, and then dive into discussion. Again, I can't hit everything, so I'm going to kind of focus on some key recommendations and just sort of a 20,000-foot view of our analysis. The initial goals of this project back in 2014 were to mainly just gain a better understanding of how tenants were using electricity in these new Xeni apartments. These at the time and still are relatively novel, using a lot of new equipment. So we wanted to understand how people were using energy and how we could improve upon that. Our more related work, which kicked in 2016, was from EPIC Grant 15-308. And this was more focused on optimizing water heating performance and went a lot deeper. So I'll be talking about that as well. I really enjoyed working on this project in part because it's just so large. Again, 2014 to 2020 was the period of study that included almost 500 apartments over 9 locations in 4 climate zones. These are demographically fairly narrow, so they're all low-income family housing. Some of them are exclusive farm worker, and one of them happens to be senior housing. They're all very energy efficient, all electric Xeni. Most of them are at least 100% Xeni, some going above and beyond that. They're significantly above Title 24 code, up to 45% above code. And for the most part, especially the ones we'll be talking about today, they're unitary systems, unitary HVAC and domestic hot water. We do have 2 sites that are central combined systems, which are essentially 4-pipe systems driven by an air mech. And then we do have 1 site that has unitary mini splits with central domestic hot water. Here's some pictures of the sites just to give you some context. They're all really beautiful, beautiful sites. As I mentioned, we started way back in 2014 with a pilot. This was focused mainly at sort of just making sure instrumentation was working correctly, and studying a couple end uses. Over the next 5 years, we studied everything from cooking to heat pump water heaters to plug loads and lighting. And then with our more recent work with this EPIC grant, we had the opportunity to sort of simultaneously study pretty much every end use for all of our tenants. I mentioned this is just a lot of data we've been collecting. So we were collecting second-by-second resolution over 6 years for current voltage and phase angle, in addition to a lot of metadata, energy models, photos and on-site observations. And then more recently with our EPIC work, we were collecting water flows, tank temperatures. We got tenant billing data. We took some tenant surveys, and we even deployed on-site weather stations as well as getting in-unit temperature and relative humidity data. On the top right, you'll see a picture of our instrumentation. So we were the data collection unit was actually behind the electrical panel, and then it's tied to an in-unit energy monitor that the tenants can see their power and daily energy usage. So before diving into the sort of quantitative stuff, I think the most important thing is that people really like their homes and they're comfortable. So this is preliminary survey data from Cloverdale. We have more surveys to administer. Coronavirus kind of got in the way of that. But for the most part, people really like their homes. The average rating out of 10 was 9.3, and the median rating was a 10 out of 10. And as far as HVAC and domestic hot water performance, most people didn't have any problems with it. They rated them very highly in both the winter and the summer. I do want to come back to sort of a 20,000-foot view, though. Even though these are really efficient homes that perform fairly well, the most sensitive variable is still human behavior. So this is a plot of whole house energy usage broken out by both occupancy and apartment complex. And even within our lower occupancy households, we have up to a factor of 5 from lowest to highest users. We have 1-bedroom apartments that use more energy than their 4-bedroom counterparts of the same complex. So again, even though these are really efficient apartments, no matter what, we're always going to have this relatively intractable variable of human behavior to deal with. Behavioral savings can have some impact, but they only go so far. This is the same data, but just for cooking as an end use. I like this one because it's a dedicated end use that doesn't really have any efficiency impacts. It's purely behavioral. And among similar occupancies, we see, a 10-fold difference between our lowest and highest users. You'll notice that Lakeport is kind of an outlier. Again, this is senior housing. And so the demographic sensitivity to this particular end use is something that our models just did not do a good job of capturing. So moving on to sort of seasonal characteristics, this is sort of a really zoomed out view of all of our unitary sites from 2014 till pretty much a couple weeks ago. It's not controlled for occupancy. It's just a straight average across the apartments. But the main point is I wanted to show sort of the seasonal sensitivity to energy usage. In the winter and the summer, we have very different problems. Our winter increase is driven primarily by domestic hot water, which I'll talk about. And in the summer, we do have a base increase, but the largest spikes are mostly due to long extended heat waves, particularly the second and subsequent days. So again, coming back to climate change and moving into the future, I want to really drive home the point that even though these are really efficient buildings, when it gets really hot, we're still seeing nonlinear increases in people's cooling energy, which is something we're going to have to deal with more and more moving forward. You really see this in terms of one of our sites, which is relatively coastal, so it doesn't get super cold, but does get cold in the winter. We found that at most of our sites, an efficient building can mostly eliminate space heating loads. You can see there's not a lot of sensitivity to energy usage in the winter, but we are very sensitive to that in the summer. This is just fan coil run times. So in the summer, when we get into those really hot heat waves above 100 degrees, our average usage, our average run times for fan coil usage is above 12 hours. But in the winter, there's almost no sensitivity to that. And I think that's sort of testament to how well designed these homes are. This is another site. I'm sorry if you can't really see the x-axis. We've got hourly temperature relative to condenser heating and cooling energy. So this doesn't include fan coil. This doesn't include any sort of parasitic loads on the system. This is just heating or cooling energy. This is at Atascadero, which is more inland, so much larger temperature swings, not as coastal, colder winters, warmer summers. And still, we don't have a lot of sensitivity to cold temperatures. But as we start getting really warm, everybody starts turning on their cooling, even at a really efficient apartment complex like this. Crankcase heaters are a significant but avoidable load. So at one of our sites, we noticed higher than expected energy usage pretty much year round, even in the shoulder season. This plot shows sort of that disaggregated crankcase heater load in blue, and then the heating and cooling energy in orange. As far as total annual usage, the crankcase heater baseload made up about half of the total energy. So that translates to roughly $180 per year per tenant. Digging in a little bit deeper, we found this was probably mostly unavoidable. Similar site at Dixon, which did not have this crankcase heater baseload, had significantly lower energy usage, especially in the shoulder season, even though it was more poorly insulated. It was in a hotter climate zone, and really should have performed worse on all accounts. When we looked at actual weather data from this site at Atascadero, we found that with different equipment, we probably could have avoided 90% of this crankcase heater baseload and saved tenants about $150 a year. So this is just one example of something really easy that was completely, wasn't really on our radar in the design phase at all, but was a really simple switch that could have saved people a lot of energy and money. So moving on to heat pump water heaters, this is a plot of occupancy, heat pump water heater energy on a daily basis relative to occupancy. The one on the right breaks that out by the resistance element recovery load and the heat pump base load. We found pretty quickly that a lot of the units were installed incorrectly. So they were installed in resistance only mode, which meant that the heat pump piece of it wasn't running at all. And this includes 43% of units at King City. Again, a really simple change that just, wasn't taken care of at install, but had a huge impact on energy use. Secondary to that, in our early installations, we found that 50-gallon tanks were not enough, particularly in the winter. Later installations included 80-gallon units, which did help some, but it really wasn't until more recently when we started putting in thermal mixing valves and bumping the set point up to 140 that we really started to see improved performance, especially in the winter. So you can see the impact on winter performance for heat pump water heaters. The top plot shows sort of a monthly trace of average demand for all our apartments, and the bottom one shows the daily 15-minute demand, maximum demand average across all apartments. In the winter, we kind of have three different things that are really combining to make sort of a worst case scenario. Now, all of these heat pump water heaters were installed in semi-conditioned space. So in the winter, we have, first of all, we have colder incoming water temperatures. So the temperature deltas we're trying to hit are much larger. We also have to mix with more water to get to a temperature that we want to hit. So maybe 105 degrees for a shower or whatever. Secondly, it's colder, so our thermal losses are greater. And finally, our COPs are also significantly lower just because of our colder air temperature. So in the winter, we might have a COP of 2, and in the summer, we might have something greater than 6. So the amount, the lift that these heat pump water heaters have to do to heat the same amount of water is up to maybe 5 times as great. So one of the things we did to sort of deal with this, in the winter at least, was just try to keep the tanks as hot as possible to have as much of a thermal storage buffer as possible. So these two plots show the average demand for these heat pump water heaters at Atascadero, broken out both by resistance and heat pump compressor energy. The top plot is sort of an out-of-the-box, factory conditions. So they were installed at 125 degrees in energy saver mode. And the bottom one is what we ended up on after a bunch of experimentation, which was heat pump only mode at 140 degrees. So even though we were running them at a much warmer temperature, which might have been overkill for a lot of our units, this reduced not only total energy, but daily demand, greenhouse gases, costs, et cetera, for pretty much every. So this was the most effective way in reducing not only peak, but total demand in the winter. In the summer, a lot of the problems that I mentioned, we don't really have similar issues. We actually have more heat than we really need, but we still found that keeping them 140 degrees at all times was hugely beneficial. So this is a plot from this last June. We found that we could keep the heat pumps at 140 degrees for most of the day. And then to reduce grid strain during peak hours, we could essentially kill the units by setting them back down to 115 degrees, but put them in energy saver mode so that the highest consuming tenants wouldn't run into issues if they did deplete their tanks. Then when the peak ended around 9 p.m., went back up to heat pump only mode in 140 degrees. And for the most part, we're able to completely eliminate that 4 to 9 p.m. demand. So two very different strategies, summer, winter. I'd encourage you to read our duck curve paper if you have time. This goes into a lot more detail. And then finally, we found pretty quickly that recirculation pumps should be avoided with these heat pump water heaters. First of all, at Atascadero, we had installed occupancy sensor-driven recirculation pumps, so IR sensor by each sink. This posed a problem because they would go off a couple hundred times a day, so we were recirculating water unnecessarily, which was just reducing the efficiency of the system. Secondarily, we found that even if they were working properly, recirculating warm water back into the bottom of the tank was sort of messing with the factory settings on the heat pump water heaters. A lot of them need sort of a stratified tank to drive, to estimate demand. And this was just causing problems for the operation of the units. We ended up removing them last November, and almost immediately there was a pretty large change in performance. So kind of bringing it all back together, the contribution to total demand varies significantly seasonally. So in the summer, I mentioned we have this late afternoon HVAC peak as people are turning on their air conditioning. This kind of continues until 9 p.m. When domestic hot water starts to ramp up as people are depleting their tanks and resistance energy is kicking in some cases. In the winter, we have a much different problem. It's pretty much primarily driven by our heat pump water heaters, particularly, again, by high-end users who can't keep up with demand. Around 8 p.m., that makes up 50% of our total demand just by domestic hot water. And we also have similar problems during the shoulder season just because of colder incoming water temperatures and lowered performance as well. I will mention that these plots from Atascadero are before we started experimenting with thermal load shifting and optimization. So they sort of represent an unoptimized stacked load shape for these apartments. One thing you might have noticed from this last slide is there's a significant amount of base load we still have to deal with, even though there are things driving the peak. And plug loads in particular are something that are relatively intractable. There's not a lot we can do to shift those loads other than battery storage. This plot shows the average demand for King City and Oxnard plug loads and lighting. And even though the averages are pretty tight, this is mainly to drive home the point that both people's parasitic loads and base loads, as well as like when their plug loads peak, is highly variable, even from day to day and across different apartments. So we're still always going to have to deal with this kind of stuff, even if we can, make significant improvement in terms of efficiency and when we're using energy of some of our dedicated end uses. So I'm not going to go into all these recommendations in detail. I'd encourage you to read the paper, but in general, we found that our simpler systems did work a lot better. Because we were constantly involved in this process and able to sort of make changes and monitor things, we caught a lot of things that otherwise wouldn't have been caught. And so some of these projects may not have been Z&E otherwise if we hadn't been constantly monitoring. I talked a lot about the need for increasing thermal storage. This can be a way to reduce risk, and often the benefit is greater than the cost in terms of just oversizing tanks and hot water storage. Mixing valves aren't that expensive, and most heat pump water heaters can go up to 140 degrees or even 160 degrees now. And designing for the worst case scenario, especially for heat pump water heaters, was the way to go. Our models aren't perfect, and we're still learning a lot with these new technologies. So definitely designing for winter performance and high consumption coincident demand was the way to go. As far as just more general recommendations, again, I mentioned that sort of constant verification was why these projects were so successful. And I think a more active rather than a passive approach to operation maintenance is key. Even in our simple systems, we were constantly making tweaks and improving things. And once we figured some of those things out, we increased performance significantly. But in our more complicated systems, ones I didn't really talk so much about today, our central systems, had we not been there to sort of monitor things, it would have been much more of a mess than it was otherwise. And tenant comfort would have been significantly impacted. So I'm always an advocate for more data. I think we need to take a much more active approach to monitoring these types of novel systems as we move forward and as the baseline, as the target keeps moving. So I'll end it there, and I thank you all for your time.
Thank you, Greg. All right, so if you have any questions for Greg, do feel free to put them in the Q&A box, but we will answer them at the end. So our next speaker is John Proctor, who's going to talk about variable capacity heat pumps, design options, trade-offs, and pitfalls. John Proctor, PE, is recognized for practical energy efficiency applications based on field studies and intensive performance monitoring. Mr. Proctor is one of the original House as a System gurus. He insists on accurate data to evaluate the true performance of equipment, systems, and field applications. His side jobs include inventing, sculpting, and rowing, and one of the products he's produced is the CheckMe, an integrated quality assurance system that combines the human experts with AI in real-time contact with field technicians for HVAC and other systems. John, I'll hand it over to you.
Okay, thank you very much. So I'm going to talk to you about the CVRH program, which was the Central Valley Research Houses. These started with something Greg talked about, which is simple deep energy retrofits, which decrease the cooling energy for these 4 houses of different vintages by up to 75%, and the heating loads in the 2 older houses by 54%. These houses provide a very great research tool because of their different sizes and their different vintages. I wish I could see you all. It would be great to see you. I did see a few names like Scott. How are you doing? Hope you're doing well. We're going to talk about the variable speed heat pump work that was done on these houses over a number of years, sponsored by the Energy Commission and Pacific Gas and Electric Company and Southern California Edison. And the work was done by Bruce Wilcox, Proctor Engineering Group, Chipwood Energy Management, Mike McFarland, Frontier Energy, and Keith O'Hara. Central Valley Research Homes got rid of one of the problems that Greg was talking about, and that is people. So what we did is we put some very reliable people in the house, which are known as computers, which produce ventilation, temperature setting, thermostat settings, sensible loads and latent loads, which are consistent. So the houses consisted of the newest house, which is the Caleb house, the oldest house, which was the Grange house, which is another slab-on-grade house, and then the next oldest house, which is Mayfair, which has a crawl space. Okay, each of these houses has at least two systems. They're both contained within the building shell. And as a result, we can do flip-flop measurements and compare two systems over whole seasons and whole years. And these alternate every few days. For some reason, I'm not changing slides easily. The analysis, one of the analysis of the mini, includes comparison of the normalized annual energy use. So this slide shows that what we did is we regressed the average daily outdoor temperature versus the average daily daily energy use. And so the blue lines are the reference system, and the green are the variable compressor heat pumps. So this gives you an idea of how many systems were test systems. That doesn't include the reference systems, and this list only goes to 2017, and the experiments are continuing. So there's no way I can cover this in the time that we have available. There's no way to even cover it in the paper. So I encourage you to at least read the paper and preferably go into the individual reports that are referenced therein in order to learn the intricacies of these tests. The first year was 2014, installed in the spring of 2014. These were installed, designed, and commissioned by local contractors who were authorized to do that work by the manufacturers and distributors. And they're perhaps closer to what one would normally expect than what we will get later on when the manufacturers were deeply involved in the design and installation and commissioning. So we'll talk about two of the houses. Grange, the oldest house, had a 3-head ductless system, 2 bedrooms and the main room with constant indoor fans. And it ends up in the end that it had low refrigerant. And Mayfair, you had a constantly running indoor fan on a ducted system. So the difference in SEERs between the reference system and the experimental system would indicate that Grange should have saved 30%, but it didn't. And indicate that Mayfair should have saved about 25%, and you can see that actually increased energy usage by over 60%. If we back out the continually running fan, which has always been a bad idea and continues to be a bad idea, then it comes up to about 10% savings. In 2015, the manufacturers were keen to show that they could do a much better job. The systems were specified, installed, and configured in the control settings commissioned as specified by the manufacturers. What this resulted in is 3 installations, 2 in particular, that did a very good job of sensible cooling, but had almost no latent capacity whatsoever. And as a result, you can see in Grange and Mayfair, where the relative humidity exceeded 60%, 39% of the time at Grange, and 23% of the time at Mayfair. Here's the relative indoor humidities at Grange. You can see that they With the reference heat pump running, they hardly ever exceed 90%. But with the variable capacity heat pump, variable compressor speed heat pump, you can see that they exceed 60% quite a bit of the time. So this also causes us to have to make corrections in order to compare the reference system and the variable capacitor system. One would have to normalize to get the same amount of latent and sensible performance. And once one does that, we get different answers. Caleb, the largest house, expected cooling savings from SCER would be 34%. With the transfer fans, so what I didn't mention already is that there were a number of changes, including putting high efficiency ducted transfer fans in the ductless houses. So there were transfer fans in Caleb and Grange to try to move air into the rooms that did not have the heads. But these are not your standard transfer fans. So if you change to the energy used by standard transfer fans, you see you go from an energy savings at Caleb from 41%, which is what is nice, to an increase in energy use of 9%. Same kind of problem at Grange. Now, Mayfair ran a continuous fan, which also is a problem. And if one goes to an auto fan, you go from 21% increase in energy use to 11% savings, which is in line with what the SCERs would indicate. Summer peak. In Caleb, where we had the same size capacity units between the variable capacity unit and the reference, we have a peak reduction of 49% with a variable capacity heat pump. We have nice reductions in all three locations. But the big caveat here is the fact that these units in this particular time actually operated as we would have expected them to. However, they have the possibility, and we've seen it at other times, of ramping up well beyond their rated capacities and having much larger watt draws. And so it's real important that these units be able to be controlled, that their compressor speeds do not ramp up during peak. The other peak issue, of course, is, as Greg mentioned, the people. So we simulated the people who come home and turn their thermostat down. So they turn it up when they leave and turn it down when they come back. These people actually hate utility companies and the California independent system operator. So the blue dots are on constant thermostat days, and you can see how the peak is higher for the reference system than for the variable capacity system. You can also see the effect of slamming down the thermostat when you get home at 5 o'clock. And those are the red triangles, so you can see the big problem associated with that kind of behavior. Now, another test, which I wasn't going to talk about, but another test that we did was we tried pre-cooling, and it ended up that pre-cooling is a really big winner, and we should be doing a lot of that. In this system, these systems were operated optimally for comfort. So the interior doors were open all the time. We had high efficiency ducted transfer fans. And nevertheless, in the largest house, the set point in some of the temperatures in some of the rooms exceeded the set point by over 3 degrees, 48% of the time. Grange, better, smaller house, smallest house actually, still exceeded the set point by over 3 degrees, 10% of the time. In Mayfair, the ducted system worked quite well as far as cooling particular areas. Now, as I said, I can't cover all of this, so I'm going to give you a quick summary here, and then I will go through as many of these as I possibly can of the final slides. So in 2016, 2017, some of the tests were the difference between ducted and ductless systems installed in the same house, in the same houses. Default settings on the variable capacity heat pumps versus the manufacturer's selected controls, and testing with interior doors closed. In 17 and 18, we looked at downsizing, okay, 2 different size units in the same house, in the same houses, and revised versus default controls. In 2018, a 7-headed ductless system in the largest house versus 2-headed ducted systems versus rep. So 3-way test in 2018. So again, I suggest that you read the paper and the reports if you really want to know about this stuff. I have some minutes left. So finally, these units have high potential, but you can't just drop them in and expect them to do what you want. The ducted systems can be put in closets and drop ceiling hallways with short runs to various rooms, provides really good distribution of cooling and heating. The continuous indoor fans are a massive problem. Continuous indoor fans should never be used. Each indoor head should be controlled by a thermostat separate from the head. One or a couple of ductless heads in a house will not adequately distribute heat or cooling to the whole house in an ordinary size house. If a very small house, it possibly can. Transfer fans don't do very much for comfort, and they use excessive amounts of energy. Multi-splits, in other words, a single outdoor unit with multiple indoor heads, often continue to distribute refrigerant and heat to rooms, overheating them. Controls are poorly documented, very difficult for the technician to access, and we need to have access to the controls to accomplish electrical peak reduction. We can't just let them go willy-nilly off and ramp up to extremely high speeds. Installation errors aren't easily discovered by technicians or inspectors. Manufacturers need to provide a test mode in order to make these really a good option. The ratings, SEER and HSPF, don't do a good job and cannot be compared to the single speed units. So a new test method is necessary in order to be able to have a good idea of what these units will do when they're actually installed. They often operate at speeds higher than necessary to meet the load, which causes more cycling, which lowers their efficiency. Many of the systems tested had a tendency to overcool or overheat the house when the outdoor temperatures were mild, but failed to satisfy the set point during more extreme outdoor conditions. And by the way, there's winter usage data in the paper as well as in the report. So there's also winter results. In 2016, you can see that there were these, the variable capacity heat pumps were installed with factory default control settings. And in that case, the latent cooling was adequate. They operated with the indoor interior doors closed, and the ductless systems, again, did not meet the comfort criteria. The savings in that year, Caleb, the largest house, expected 33%, with no fans, it was 27%, but with the fans, it was minus 10%. Grange expected 52, got 46, but with the transfer fans, 9%. Mayfair, 33%, no fans, 23%, negative savings, 18%. In Grange, both the ducted and ductless systems in 2016 ran very short cycles. The shorter than 10 minutes, 50% of the time. And by comparison, the same size unit the previous year from a different manufacturer had 80% of its cycles that were 90 minutes or more. So you had a short cycling problem there at Grange in 2016. This also shows that Mayfair, during the summer here, when the outdoor temperature dropped, all of a sudden the unit, when you got below 75 degrees, for some reason decided to go to terribly inefficient mode. So this is the EER, the measured EER at the unit, and you can see that below 75 degrees, we suddenly drop off into low efficiencies. The same kind of efficiencies that you get at 95 degrees outside. This is a comparison of ducted versus ductless systems, and the temperatures, the comfort, you can see, and this is heating comfort we're talking about now. You can see that the ducted system, for example, gives you better comfort control over the ductless system. And same thing in all of the houses. And with respect to savings, you can see that, again, in the winter, we expected a 21% savings at Caleb. We got a 30%, a negative 30% savings. Okay, these are similar downsizing. We found that if you vastly oversize a unit, one of these variable capacity units, then there's a big savings in getting down to closer to the right capacity. If it's oversized by a little bit, no, it doesn't make a lot of difference. The factory default settings were not necessarily optimal, and we could make improvements on those. Okay, so that may not be the end of the slides, but it's the end of my presentation. And thank you very much.
Great. Thank you so much, John. Again, if you have any questions for John, you can put them in the Q&A box, and we will talk through those questions at the end of all of the presentations. So our next presenter is Catherine Daham, who will be presenting about dual fuel space heating in cold climates, optimizing cost emissions and grid flexibility. Catherine helps the U.S. and global clients analyze and cultivate emerging clean energy resources at the grid's edge. Her research is focused on identifying impactful ways to save energy and reduce carbon emissions, and has contributed to deep energy savings throughout utility programs and energy efficiency regulations. Her recent work has delved into beneficial electrification topics such as electric vehicle load control and electrified space heating. She holds a Bachelor's of Science degrees in Environmental Engineering from the University of California, Berkeley, and a PhD in Geophysics from the University of Colorado at Boulder. So take it away, Catherine.
Okay, thanks, Sharon. And I'm excited to be here and presenting our work on starting to electrify space heating in a totally different climate than we've been talking about earlier in this session, cold climates of the US. So I want to acknowledge my co-authors here, Kat Merci here at Exergy Consulting, Robin Roy of Next Energy US, and Keith Dennis at NRECA. This project was funded by the Beneficial Electrification League, NRDC, and NRECA. Okay, so this work was motivated by, I'm sure what motivates a lot of you, the need to address our current climate crisis through deep reductions in greenhouse gas emissions. And that means not only cleaning up our electric grid and using variable and renewable generation resources, but also electrifying those end uses that currently use fossil fuels. So in the residential sector, space heating is a major target and accounts for almost half of residential site energy use in the US. And particularly in cold climates, only about 10% of space heating is electrified today. But we don't want to just electrify to electrify. We want to do this transition in a strategic and beneficial way. So that's the idea behind beneficial electrification. So these are strategies that achieves at least one of the four things on the screen here without negatively impacting the others. So it's something that saves consumers money over the life of the product. It reduces emissions to the atmosphere. It's a load that's flexible to the grid, so it can shift its operation to periods of time where electricity is prevalent and less expensive. And it improves the consumer experience in some way. So for space heating, that might be improved comfort in the home, or it might be improved air quality inside because you're not burning the fossil fuels in the building. So there are a few options for electrifying space heating. And in this project, we actually honed in on air source heat pumps for a variety of reasons. They're quite efficient because they move rather than produce heat. They're experiencing increased adoption even in cold climates, thanks in part to efforts by folks at NEEP in the Northeast and CEE in Minnesota, who are really promoting these technologies to consumers and utilities. And they also have lower installation costs than ground source heat pumps, which are really efficient, but expensive to install. Air source heat pumps do have challenges, though, particularly in cold climates. First, they're not a terribly flexible load. Heat pumps are most efficient when they can operate at a constant set point or just kind of small setbacks of a few degrees or less. When they have to recover from large setbacks, they're running compressors flat out and not very efficient, and they take a long time to recover. Also, their performance decreases with temperature since they're pulling heat from the outside air. Standard models start to decrease in their performance when outdoor temperatures are in the 40s Fahrenheit and can't operate below about 30 degrees Fahrenheit. Cold climate models are an improvement. They have variable speed compressors. They can provide their full capacity down to about 5 degrees Fahrenheit and even operate down to negative 13 or negative 18 degrees Fahrenheit. So that's an improvement, but the places in the US that experience really cold temperatures get a lot colder than that on a daily and basis and during extreme cold events like polar vortices. So there's not really any avoiding the need for backup heat to go along with air source heat pumps in cold climates. That might be electric resistance, which would add a lot of load to an already stressed grid in really cold times. But there are other combustion solutions like furnaces and fireplaces. So for this project, we honed in on looking at central ducted air source heat pump systems that use a central furnace as backup. And we wanted to look at the benefits of these dual fuel systems compared to fossil fuel furnaces from a cost and emissions perspective. And we also wanted to look at the value of dual fuel systems compared to all electric ones in terms of grid flexibility. So we developed a model that calculates these benefits on a high-level regional basis as a first step to start to understand where these dual fuel systems could be beneficial, with the idea that our future work could add more detail to the model and refine it where dual fuel systems look more promising. So here's a sketch of the ducted dual fuel system. It consists of a heat pump, the indoor and the outdoor unit, paired with a furnace on top of an air handler, which blows the return air over the heat exchangers of the furnace or the heat pump and out into the duct system. We considered this system in a couple of different installation scenarios. The first was a replacement scenario where the existing furnace has reached the end of its life, so it's replaced with this whole system. And we also considered the case where the furnace might be relatively new, have a lot of life left. And so we're just adding the air source heat pump to that existing furnace. We made these calculations for both standard and cold climate heat pump models. Now we are assuming in the model that we have, this works perfectly. So we have the controls that'll orchestrate all these components and make sure that each one is operating when it needs to. We're also assuming that the air handler can vary its speed to match either the furnace or the heat pump output. Now in practice, this is actually still quite challenging. In reality, you probably need to have components from the same manufacturer to get this to work right now. The all-electric system that we looked at is very much similar to the dual fuel system, except there's an electric resistance heater instead of the furnace for backup heat. The calculations are described in detail in the paper, but at a high level, they're driven by an assumed temperature-dependent heating load for a typical home and hourly weather data from a heating season. We carry out calculations both at Northeast and Midwest locations, and the heating equipment is sized to meet 100% of the heating load of the home. We do need to make some key assumptions around performance and efficiency of each heating component in order to calculate the estimated energy use of them as they provide the heat to the home. So the heat pump has a temperature-dependent coefficient of performance, COP, which is the heat delivered divided by the electricity consumed to do it. That applies to the indoor and outdoor unit and is from manufacturer spec sheets. We reduce the COP by assuming a defrost cycle. So these air source heat pumps must run a defrost cycle when temperatures get low to prevent frost buildup on the heat exchanger in the outdoor unit. And that's a hit on COP. So we have a COP penalty for when temperatures get below freezing. In reality, this is really going to depend on the field performance, and so field measurement of how these systems are working in the field is going to be really important to refine these estimates. We have some furnace efficiency assumptions in the replacement case where changing out an 80% baseline furnace for a high efficiency 95% furnace. When we're just adding on the heat pump to an existing furnace, we're assuming it's already efficient. And we need a knob to decide when each component is going to run in the calculations. So for this set of calculations, we're showing, we're basing that switch on the temperature. So we're operating the heat pump where it can efficiently deliver the heating load of the house. But when it gets too cold for the heat pump to do that, we're operating the furnace. So for systems with cold climate models, that's -5 degrees. And for systems with standard models, that's 30 degrees. And finally, we're assuming here just some regional flat rates for fuel costs and emissions. We can certainly build that out in the model with time varying costs and emissions later. And we're using initial costs from NREL and manufacturers, but we found that the cost for the equipment is highly location dependent, varying from region to region and even contractor to contractor. And so that's a major source of uncertainty in our calculations. And based on feedback we've had, if anything, we're underestimating initial costs. So just bearing that in mind as we look at some results here. First, let's look at energy costs. So this is 8 different scenarios that we ran in the model in the Northeast and the Midwest regions for the dual fuel or all electric systems with either a standard or a cold climate heat pump. The horizontal dashed lines indicate the energy cost associated with the baseline furnace, either 80 or 95% efficient. And the columns, the blue part of the column represents the cost of the electricity that the system consumes, and the black is the fossil fuel cost. I should mention that we assumed in the Northeast the fossil fuel is fuel oil, and in the Midwest it's propane. And we did run these calculations assuming natural gas, but the economics are even harder than these higher cost fuels. So we can see here that the dual fuel systems are actually cheaper to run than an 80% efficient furnace, and in some cases cheaper than even a 95% efficient furnace. So we did a simple payback analysis, and we found that the cost savings on an annual basis doesn't really add up to enough to pay back the initial investment for many of these systems, with the exception of the dual fuel system with a standard heat pump, which is just, it's costs less to in first costs. Moving on to the emissions benefits, here we see in the Northeast clear benefits of the dual fuel and all electric systems compared to the fossil fuel furnaces. The Northeast the grid there already has a fairly low emissions intensity, whereas the Midwest grid is about twice that of the Northeast, and therefore right now the emissions equation doesn't really pencil out for dual fuel or cold climate systems there. But we do want to be looking at emissions over the lifetime of the product to factor in the fact that the grid is going to get cleaner through time. So we haven't built that into the model just yet, but we did run the same scenarios, assuming the grid is half natural gas and half renewable generation. And you can see the Northeast is almost to that point as far as emissions intensity goes already. And as the Midwest moves towards that, the emissions benefit of dual fuel and all electric systems will become net positive. So finally, let's look at the flexibility of dual fuel systems, because I think this is really a great value of them in cold climates. So like I said earlier, these regions can experience extreme cold events that are many days long. And so we need to have a system that can provide heat and comfort to these homes during these extreme cold events. So this is a temperature record from Duluth, Minnesota, for the polar vortex of 2019. And looking at what the all-electric systems are doing through this event, the system with a standard heat pump can't even run the heat pump because the temperatures are too cold. So this is basically an electric resistance heater. And you can see it's drawing 8, 10, peaking at 13 kilowatts through this event. The all-electric system with the cold climate heat pump can do a little better. It's running the cold climate heat pump when it can and supplementing with electric resistance, but it does get cold, gets cold enough that it eventually has to just run the electric resistance heater, and again peaking at about 13 kilowatts. The dual fuel system, on the other hand, with the cold climate heat pump, we have it set in our calculations to run the furnace below -5 degrees. So in this case, the dual fuel, the heat pump portion of that system wouldn't even be drawing any electricity. We'd be running the furnace through this event. And I should say that the dual fuel system can be optimized, not only by temperature, but it could be optimized to operate at the lowest cost or the lowest emissions, or whatever best suits the current conditions on the grid. So I think this is the real value of dual fuel systems. So to summarize, we see good potential for dual fuel systems in cold climates as far as grid flexibility goes, definitely, emissions definitely in the Northeast and potentially in the Midwest, if not now, then potentially soon. And where it's really challenging is the economics. So based on simple payback, we only see benefit for the scenario where we're replacing the furnace with a dual fuel system with a standard heat pump. Now, we did ask the question, what do the economics look like if the consumer also wants air conditioning as part of this measure? So if we're subtracting out the initial costs of a standard air conditioner, we're now getting that the cold climate heat pumps and that dual fuel replacement might actually be cost effective as well. So in summary, dual fuel systems in cold climates are looking like a pretty promising strategy for partial electrification of space heating. We see this as a bridge technology toward full electrification, where we can electrify a good portion of the space heating load now while we're working to electrify the rest of it in the future. There are still some research and development needs that go along with deploying these dual fuel systems. Most notably, compatible controls and air handling to make the system work as we've modeled it in these calculations. Of course, we need a better understanding of the field performance, like the work that Greg and John are doing in California. And also folks at Slipstream and CEE in the Midwest are doing a lot of work on field performance in cold climates. In the model, we need to do more of a localized assessment with forward-looking parameters. And we already know that the economics is going to be a significant barrier to overcome. But, in this work and also the work of everyone else in this panel, I think what it's really coming down to is that we need a holistic approach. We need to be able to reduce the load of these homes so that we can address as much of the load as we possibly can with clean electricity. So that means de-weatherization and air sealing measures and energy efficiency measures on all the other loads in the home. And finally, we've only looked at one electrification strategy for space heating in cold climates, and we should be checking them all out so that we understand what the best solution is depending on the application. So I'll leave it at that. Thanks for being here. My email is here. If you have any questions, feel free to reach out. I also want to say thank you to Vladimir and Sharon for organizing this panel, and to everyone at ACEEE behind the scenes putting this whole conference together. So I'll now pass it back to Vladimir for the Q&A.
Thank you, Greg, John, and Catherine for excellent presentations. We have a few minutes left in the session, and we have a lot of questions that came in. So we're going to try to answer a few of them, but probably not going to be able to get to all of them. So I'll take the questions in the same order that how the presentations were done. So let's start with Greg. Do the controllers on the heat pumps allow for the remote software update like you would see in Teslas? Hi, Greg, are you on?
Yeah, sorry, I had myself muted. So the units we were working with were Ream Prestige, so they have bidirectional capability. So we're both pulling data remotely and making changes to set points sort of on the fly. Now, I don't know how Ream does their firmware updates, but you can definitely update remotely.
Okay, excellent. Another question for Greg. On recirculating heat pumps, instead of using occupancy sensor, if it was a user button controlled recirculation option, how would it change what you were talking about in terms of energy savings and water savings?
Right. So after we removed the occupancy, the IR-driven sensors, we installed push buttons at each sink. Turned out that nobody used them anyways, even though we left some literature on how to use them. But later we found out the manufacturer cautioned against using recirc pumps altogether just because of some of the issues that it caused with stratification and the way that the water heaters sort of estimate demand to turn their compressors on and off. So in general, I think it's discouraged, but we don't have really much data to back if there was other methods of doing that better.
Okay. There are a couple of questions on crankcase heaters. Can you quickly maybe talk about what it is, and then what are the solutions to avoid that issue?
Yeah, so I'm not an HVAC tech, so this isn't my area of expertise, but the main point of the crankcase heater is to keep the refrigerant from mixing with the oil inside the compressor, especially during colder temperatures. So if the thing is sitting idle for a period of time and there's mixing that happens, it can cause the compressor to seize up and kind of ruin the device. So I've been looking a little bit to see if a lot of manufacturers don't have a lot of information on sort of aftermarket or installed controls to only turn these on when they're below a certain temperature. But there are different types of compressors, like scroll compressors, for instance, that don't seem to have this same problem. But again, I don't know if I mentioned this. This sort of parasitic load isn't rolled into like the SEER ratings, as far as I know, for these units. So it's not something that manufacturers really care about because it's a really cheap way to prevent device failure.
Okay. Thank you, Greg. So let's switch to John. John, the first question for you was, were you able to gather part load performance data? Let me say part load performance data, efficiency as a function of part load ratio from the manufacturers, and then validate that with field data?
Yes, we were able to gather tons of part load data, and no, it doesn't correspond to what the manufacturer's tests and data show.
Can you elaborate a little bit as far as how much off, and do you know why?
Well, one of the big reasons is the way that these things are controlled. They ramp up real fast at the beginning of the cycle, then they eventually slow down. By then they've overshot and they have to shut off, and then they cycle again. And it's all a controls issue. I mean, all that's the controls issue. They don't go according to the way you would think they would work. That's not how they work.
Is it connected also to the oversizing you were talking about, or is that completely separate?
No, I mean, even with proper sizing, we have the same problem.
Okay. Another question is a more general question. What design or control considerations should we consider to maximize savings for variable capacity systems over fixed speed systems?
Get the fan to cycle on and off with the compressor, number one. And number two, read every single thing the manufacturer puts out and try to look at the different control methodologies they have, which are difficult to understand. And you might come across something that actually works. The report talks about that quite a bit.
Okay, so it's kind of building on the previous question, but if you have additional insight. So why do you think the systems operate at higher speeds than necessary? Why do they go up into,
I have to guess what the engineer who decided to come up with the algorithm had in mind. And frankly, I don't get it.
Okay, that's good enough of an answer. So you've mentioned a little bit about pre-cooling to mitigate recovery loads. Can you recommend this, for homeowners who have this heat pumps or variable heat pumps, what recommendations can you make on the use of these types of systems?
Well, my recommendation primarily really is to the utilities who, there's no particular reason for a homeowner to go after pre-cooling unless they are doing the opposite, which is being stupid and setting it the temperature way up before the 5 o'clock hour and then trying to cool down the house fast, which it doesn't do if it's a properly sized unit. So the primary thing is to pre-cool, and inside the paper not the paper, but inside the reports are the time frames that we use to pre-cool, which honestly I don't have off the top of my head. Another kind of pre-cooling that we use, by the way, in these units is whole house fans overnight. And that makes a really big difference in the energy consumption in the summer.
All right. Thank you, John. And a few questions for Catherine. We have a couple of minutes left. Catherine, minimum efficiency air source heat pumps are required to have a COP greater than 2.0 at 17 degrees F. So why are you assuming that it needs to switch over at 30 degrees?
We did actually some sensitivity tests to see where the heat pump can actually better address the heating loads in terms of costs and emissions. And 30, I'm getting an echo, but 30 degrees for the standard heat pumps was about the sweet spot there. The cold climate heat pumps were running down to -5 degrees Fahrenheit.
Okay. What electricity costs were you assuming in your analysis?
So we were just using regional flat electricity rates in the results we showed here. So those were based on EIA data. But we do have the ability in our model to use time of use rates, so we could do that. I think there is need to, if we want to make it more sophisticated, we can certainly build in more sophisticated way to deal with variable rates. But for now, we just wanted to start with something very simple as kind of a first look at whether or not dual fuel systems can actually be beneficial in cold climates.
All right, and the final question, did the baseline for your cost effectiveness calculations include cost of replacing a heating and cooling system, or only the incremental cost between a furnace and a heat pump?
Yeah, it was the incremental cost between the furnace and the heat pump. So again, very simple first take at the economics.
All right. Great. Big thank you to everybody. This was one of the first sessions to open the conference, so I think we did a good job. Again, thank you, Greg, John, and Catherine. Excellent presentations. A lot of good information. Thank you.